Okay, welcome back everybody. Yesterday we did the basic setup of our compiler. We managed to compile an empty main function, but this doesn't actually do anything, right? Especially when we manually run the compiler without the debug output, it simply does nothing. I've refactored it a bit so it doesn't print anything out on success. So this is now just the equivalent of if you just execute an empty Python file, right? It just does nothing successfully. In this stream, I plan on actually implementing the first expressions and statements so we can start doing things in the body of our function. So let's get started. There was a question in the chat, so let's answer that first. So the question is about this first type and last type and the first decal and last decal. The idea is that we can conveniently figure out whether or not an enum value is a type by doing a range comparison. So if it is greater or equal to first type and less than or equal to last type, then it is a type. And we use that in the base class. The base class specifies like it's a base class for all nodes in the range first type to last type. And that way Dryad automatically knows how to convert any node to a type. If it looks at the node kind, if it has the specified one, then it can downcast it to a type. So let's start by adding a new kind of node hierarchy to our AST, expressions. So expressions for now, we will support they call it on the standard integer constant. So integer constant, and then we also add first expression and last expression. This means that we then added another section down here. All this boilerplate we have to do once to set things up. So, and every expression has a type in C. So we in fact can copy this one over. So this is the expression. It's an abstract node from the first expression to the last expression. They don't have a name, but they do have a type. Okay, and they don't have a name. So every expression has a type. This means that we can now add our first real expression, which is the integer constant expression. This is a concrete node. What I forgot what the types are: expression, a kind, and base. Yeah, makes sense. Node kind, constant, and the base is expression. Now the integer constant stores the suffix. We ignore the suffix; they store the value. So let's store that as a uint64, the value, and provide a way to get the value. As well as write a constructor. Let me copy one. So we need the type and we need the value. And we initialize the value to value into the expression. Okay. My language was crashed, so we could start it. Okay, so we don't have a name here. Okay, comma here. So this should all be fine, except we're getting a bunch of warnings in the S printing. I've refactored it a bit since last time, so we need to add something here. Integer constant. Let me rename that to integer constant expression. And when we want to print an expression, we need to integer constant expression. We want to print the value. Okay, that's expressions. How do I run the command? Again, I have a Vim script that looks at the JSON file, parses it, and then knows what to do. If it's a custom written solution, I might publish it at some point. So those are expressions, but of course the function body doesn't consist of expressions, it consists of statements, so we need to add statements to the mix. So this adds the same kind of boilerplate. We've got basically the expression statement. This is a statement that contains a single expression, and then the block statement, which is a group of expressions. So first statement. And then we essentially copy the type one if the closest one. So let's copy this one over. First statement, last statement, and that's the last of the S boilerplate that we need. So then we have an expression statement. It's a statement. A statement that evaluates an expression. So that's an expression statement, right? The function call is an expression statement because the function call is an expression and then it's just the statement form. So this one has as its child the expression, which is code looks similar like this. So let's copy this one over. And then we cast that to an expression. And then the constructor. Insert the expression. So that's an expression statement. And then the second form is a block statement. Just statements inside the block. So that's a block statement. And a block statement is an expression statement. So statement, and similar to a translation unit, we can add shit onto it. So we can add after another statement, we can add new statements. And then we can get a list of statements, which is the children and class of the statements. Okay. So now we've got the kinds of node that we need, expression statements and block statements. We also need to add them to the S dumping. So we need to add them here, expression statement. And block statement. We don't actually want to print anything for them because by default the parsing code will print all the children. And for an expression statement, the child is the expression, so that will be printed. And for block statements, it's another set, so the dump node will just work. This means that we can now continue on with writing parsing code for that. So we want to parse expressions. So we've got the integer constant. This is the grammar for an integer constant, so it's either decimal, octal, hexadecimal, or binary. Let's just support decimal for now and worry about the rest later. So this means that we want to simply decimal digits that they are digits in decimal, and we've got a separator which is this tick sign. So this is all hard-coded. Decimal digits, but of course we want to actually don't just pass the digit, we want to get the integer value of it. So we convert those into the integer value. And then we want to create the node out of those. So this returns a pointer to an integer constant expression and takes the integer as its value. And then we're creating an integer constant expression with the value. And since we're only having integer right now, the type is int. So we create a built-in integer type. So we create a built-in integer type, type value. So we can now parse, we parse a sequence of decimal digits, convert them into UN64T, and then use that to construct an integer constant expression whose type is int, and with that specified value. This will be currently having one kind of expression, so when we pass an expression, we're passing an integer constant expression. Finally, we want to pass statements. So we have an expression statement. This simply parses an expression followed by semicolon. And then we construct the same sort of deal here. We construct an expression statement node. We get the expression statement. The expression we get as the argument. So we then simply create an expression statement out of it. And A block statement is a curly bracketed list of statements. Need to forward declare that. And to actually get them, let's just make it easier for now and say we convert them all into a temporary vector first. So this will be a vector of pointers to statements. And then here we get the statements. We create our block statement. So we create an empty block statements, iterate over all the statements in our statements. Let's actually do them like so. So because we need to add them, it's a linked list, so we need to provide the position to insert them after. So if I is 0, we don't have anything. Otherwise, it's statements I minus 1, and then we insert statement I. And that's our result. And the final piece of the puzzle is to update the body of the function. We first need to define the statement node. So a statement is either a block statement or it's an expression statement. And then we simply construct, or rather, we forward the entire thing as statement. So now we can parse statements and block statements, which means that instead of hard coding the function body to an empty thing, we simply say we want to parse block statement. Which means that we get a block statement here. We currently have no way to store it. Let's just check whether this compiles. This needs to be unsigned. I'm missing some. Forgot to update the return type somewhere. Block statement. Oh yeah, of course, this returns a block statement. And we forgot to account for the fact that this might be empty. So list always requires parsing one or more, but we might have nothing. In which case we simply return an empty block statement. Which means I need to adjust this one to be variadic. But now we can still parse the same code, but we can actually go ahead and add the file. We can add expression statements in there. So 14, for example, that's an integer literal, that's an expression statement, or 10, or we can add a subblock 1, 2, 3. It passes, but we're not printing anything because we have no way to store the block statement at the moment. So we need to add it to a function declaration. This can now also take a block, which is the body of the function. So the body of the function is, and then we're doing the same deal we did for a while now. We get the first child, we cast it to the appropriate type. Actually, we need to get the second child, because the first child of the function declaration is its type, so that a second child is the block. So this means that we get the children begin, we advance it 1, and then we can cast the second child to the block. And then in the constructor, we say insert child after the type, we insert the block. So now, when we can simply adjust the parser to function decal, when we get our block statements, we pass it to the constructor, we execute it. This isn't called block, it's called block statement. And it tells if I can type. I cannot initialize a parameter of type container, not what? Why not? So after the first child, we insert the block. And now it works, and we print a bunch of stuff. So this was the file that we are currently parsing. We've got a bunch of expression statements inside the block statement, and as you can see, every function decal now has a block statement as a child, which contains the expression statements as children, and then a nested block statement with more children. Let's comment that. Simple expressions and statements. Which means that what we now need to do is generate code for it. So, we've got, let me look at the test again. A function now has a block statement as its child, which means we need to visit it and repeatedly generate each individual statement. So for that, let's go ahead and visit the tree that is rooted in the decals block. There are multiple things we can visit. In fact, we visit the children statements. So we can visit two kinds of statements. The first one is an expression statement. An expression statement, which means we get an expression statement, or we can visit another block statement. If we visit a block statement, we don't need to do anything for the block statement itself. We just need to do something for its children. And since the children are visited as well, this works fine. But when we visit an expression statement, we want to generate code for the expression. So we want to generate code for the expression, which is done again automatically because this happens recursively. So this will be visited 2 times. It will first be visited before we visit the expression, and then afterwards again. So when we visit an expression statement, we invoke the lambda once, then we invoke the lambda for its child, which is the expression, and then we invoke the lambda again. And let's write the visitor for the expression first, so we see what we need to do. So when we visit an integer constant expression, what we want to do is we want to evaluate to that constant. So for example, the integer constant expression 14 evaluates to 14. This means that we put 14 onto the stack. It assigns it. So onto our builder, we put the value of our expression. Pushes the value of the expression onto the stack. Which means that if we have further expressions, they might use that value. But in this case, in the case of an expression statement, it does nothing with the result of the expression. It simply discards them. So what we need to do is, after we've visited an expression statement, we need to discard the value from the stack again. Which means that if we are done, so the expression statement, the underlying expression has been visited, and we need to remove its value from the stack. So we simply pop it again. And then finally at the end, we still add an implicit return 0. So that's the general idea behind the Codegen. We will visit the body of the declaration when we have a block statement. We don't need to do anything. Children do all the work. When we have an expression statement, we will visit its child, which simply evaluates to the value of the expression, which we then need to remove from the stack. So let's fix the compilation errors. I guess, yeah, the integer constant expressions themselves are always unsigned, because there's no way to express a negative number for its value. So they're always unsigned, so we're pushing in fact an unsigned here. Why are you complaining? Now I need to add a bunch more consts. Okay, and we're doing nothing. This is actually really funny. So we've written the Codegen for the expression for the body of our function. So what this now does is it pushes a bunch of integer constants onto the stack, and then because they're used as statements, they immediately discard it again because the statement doesn't produce any value. Which means that we loaf actually constant folds everything away. So we're still not doing anything. But we are in fact pushing them. We just can't see them because a loaf constant folds everything away. Let me actually jump to the source code and simply hack constant folding away. Just a thing. Now we actually see stuff. So I've just removed constant folding aloft, which means that now we see that we push 0xe, which is 14. Yes. So we push 14 onto the stack and then we discard it because, as the compiler already pointed out to us, all the expression results are unused. So we push them and then we pop them, and then we pop 10, push 10, and then we pop 10, and then we push 1 and we pop it, and we push 2 and we pop it, and 3 and so on. So this code actually works. It's still silly because we're not doing anything, but it works. So let's commit that. Codegen for statements and simple expressions. Now, we now have a more fancy way of doing nothing, but we're still doing nothing fundamentally, which is of course bad. So let's actually add a way to see the values that we're doing by adding print. Actually, like, until we reach the point where we can call print, will take a very long time because we need to support a bunch of features for that first. So let's just hack in a built-in for just printing stuff. I mean, we're writing a compiler, so we can extend the language. So let's add a new kind of statement. Built-in statement. Yeah, a built-in statement. And then we add a new node for that. Where do I have got the, let's call it Parsing statements. A statement that plus a built-in action. This is a built-in statement. We define an enum for the kind of action, built-in t, and we support print for now. So we are ready to print stuff. Built-in t, built-in. In fact, I can copy the code I did over here. So this looks very similar. So built-in statement. We have user data built-in t, built-in impl. We set impl to built-in. And then we provide a getter for that. So this is now a statement that does some sort of built-in action. We need to add a way to print that. Oh, thank you that you're actually pointing that one out. I forgot to... This would have been bad. So now that. And when we do want to print that, because we have data that isn't stored in its child. If all the data of a node is stored in its children, we don't need to do anything here because it will be printed automatically. But here we want to, similar to the built-in type, we want to say that this is the print statement. Let's call it like that. So this is the print statement. Then we're done. Should still compile. No, because I forgot to say that this is a UN16. It still compiles. Let's add it to the parser. Parser is over here. Version statement. Built-in statement. And let's just say that the built-in statement looks like, actually let's define a keyword. So we define a keyword, built-in types, and built-in statements. And we've got print, which maps to print. Then when we pass a name, we need to reserve built-in statements as well. And then we pass a built-in statement, we pass built-in statement, followed by an expression, which is like the argument to the statement. Built-in statement, built-in t, built-in. We create the built-in statement from the built-in, and I forgot to add it here that we also need like the argument, what we're printing, which is an expression. So we're printing an expression. Set insert child after, which again becomes our first child. And then we provide a getter for that. Then we say that a statement is a block statement or built-in statement or something else. Nothing changes, but we can now actually edit our file and say that we want to print 42. Oh, we forgot to pass the semicolon. Right, so now we're printing, we can see in the AST that we contain a built-in statement, print, which takes 42 and prints it, but we've got an assertion here because we forgot to handle it in Codegen. So what we're now doing in Codegen is we are visiting this integer constant expression, which will push 42 on the stack, but we're not doing anything with it. So let's say that similar to an expression statement, we want to do something once the expression has been pushed onto the stack. But in this case, we don't want to discard it. Visit it and pushed its value onto the stack. We now want to do something with it, depending on the kind of built-in that we have. And in the case of print, we want to print it. So to print it, we are calling built-in from low from now. Lib debug. And we say that we want to call built-in, and what we want to call is low lib debug print. Why do you not want this? I need to include another header. Why do you still not like it? Right. So what we want to do is we want to print it. Print the value on top of the stack, but print leaves it on top of the stack, so we need to remove it. The value after we have printed it. So now we get the correct bytecode. We push 42 onto the stack. Then we code print. Then we remove 42, we push 0, and we return. And as we can see, when we execute the program, we see that we printed 42. This is great. You can now actually do stuff, write a program that does something. So when we execute it here on the command line, as we can see, we have a program that does something. Now I want to, we can now go ahead and add the other kinds of integer types, like the standard defines a couple more, decimal, octal, and so on. We can extend them, print them, and see that we pass them and produce them correctly. But this would be boring. This would work. The issue is that we can't test that automatically. So let's add another kind of built-in statement, an assertion. Yeah, I can use that as an identifier. It's only a macro if it's after occurrence. So we add another kind of statement, and this asserts that value is non-zero. So this means that we can now edit, need to adjust a bunch of things. So when we have assert, we say assert. And in the compiler, built-in statement, we want to add another kind of built-in statement, namely assertions. So we say when we have assert. So now two kinds of built-in statements. And then in the Codegen, when we have assert, we use the test library from Love, and when we have assert, we simply assert that the value is non-zero. Now lib test assert. We're not actually using it. So we want to assert that 11 is not 0. Apparently 11 is 0. Why exactly are you complaining? Like, we're pushing 11, we're calling assert, and that fails. Huh. How is assert implemented? It's assert that the value is 0? Wait, really? Why? Apparently assert is wrong because we need to do that. This is why I'm using love in production. So, which means now that we actually got the assertion, we can assert that 0, 0. 0, 0, and we get an assertion failure. Because 0 is in fact 0. Excellent. Add assertions. Let's go. Now, of course, to actually write tests, we need to compare values, which means that we need to add our first kind of expression that, like a compare expression. We want to compare values for equality, which means that we need to have, let's call it a binary expression. This is a node, basic node of type binary expression, and it inherits from expression. And it essentially looks the same like all the other ones. So we can just copy this one. So there's an operator. In this case, we only have equal. So there's an op, and it has a left child and a right child. We calling this one the operand. So the operand will be set to op, and then we insert the left child, and after the left child we insert the right child. So the left child is the first one, and the right child is the second one. Now I need to add that over here. We have a new kind of expression, binary expression, which we need to handle in a similar way to like we handle the built-in statement or the built-in type. So a binary expression, we switch over the operation that we're doing, and if it's equal, we print out equal. The first chart. Right. Expression also has a type. So we need to also get the type. So we know what type it is. This still compiles, which means we need to add it to the parser. Part right here. Operator precedence parsing is built into Lexi. So this is an expression production. We need to specify what's the atomic operand. In our case, this is an integer constant expression because we don't have anything else. And then we need to specify like a bunch of operations. So the only one that we're currently having is equality. So this is a binary, what's it called? Infix operator that is left associative. Its operator is that, and its operand is the atom, because we don't have anything else. And then the root operation is also equality, because we don't have anything else at the moment. Then we also need to define a callback. In this case, this returns the generic expression node. And we're having two overloads. The first one, when we only have an atom expression, this will simply forward the single existing expression node. And the second one is when we have a binary expression. We get two arguments. So we will always get the... this is a bit ugly. We will always get the compiler state, so I can't use that, I have to say. So if we get a constant expression, we simply return that unchanged. This is when we only have an atom. And when we have a binary expression, we get two expression nodes, the left and the right one. What the hell are you doing, format? Oh, I'm missing a parent somewhere, which is why it's complaining. I don't know where. Oh, here. That looks more like it. So we have the left and a right expression, and we need to turn that into the proper kind. So we need to specify here, this is an operator, and its tag is CLR of binary expression equal. Then we get the left expression, what kind of binary operator it is, and the right expression. And we can use that to now construct our binary expression. So state as to create a binary expression, and its argument are, we first need the type, but we simply take the type of the left one. We will need proper type checking for that later on, but since we're only having ints, we can just copy the type of the left one, the operator, and then the left and the right child. This should be the argument. Does it compile? It does not compile, because I messed up the order. Type up left right. Type up left right. What does type return? Type. Oh. We want a mutable type here. So I can't wait for the feature where you deducing that feature. We don't need to do that anymore. Must use struct type. That is also fun. C++ is such a great language. Okay, it compiles, because does it actually compile work when we try to use the feature now? Test.c, so we want to assert that 0 is equal to 0. We get a weird assertion failure. Oh, because the type... okay. So the issue here is that we've got the... we're saying that the type of the expression is the left type. The issue with that is this will then add the type node to the binary expression as its child. So it will go binary expression for op. It has that type. it has left, and it has right as children. The issue is that the type node is already a child of the left operand, right? So this type node and this type node, which is the child of the left node, those are the same ones, and we can't have it the child of two different nodes at the same time. This doesn't work. So what we actually need to do is we need to clone the node and clone the type. I haven't implemented that in Riot so far, however. So let's just say, since we're always dealing with ints only anyway, let's just say that we create a new int node and fix that later. So we create a built-in type int, and say this is our child. And now it parses. So we got a built-in statement. Its child is a binary expression who has a left operand and a right operand, and then the type. This is the wrong order. We want the child order to be the other way. We want to have the type first, which means makes sense that we need first children front. So after the first child, which is our type, then we want the left node, and then we want to. So now we got a binary expression of type int with two operands, 0 and 0. We haven't adjusted Codegen yet, so let's do that as well. Codegen, and then we need to adjust for the case where we have a binary expression. So these are all the expressions. And in a similar spirit, like all the other code that we're doing over here, an expression pushes its value onto the stack, which means that when we visit a binary expression, we first visit it once, then we visit its children, and then we visit it again. And when we visit it again, the two operands have been pushed onto the stack. At this point, two values have been pushed onto the stack, because we have visited children, which pushed the value. Compare them. Now, we want to, we want to switch over the kind of binary expression that we're having, but since we're only having equal, we compare them. Which means we need to check whether they're equal. The issue that I just noticed is that Love has instructions for comparing integers, but they are three-way comparisons. So they give you -1, 0, or 1. We want 0 or 1, depending on whether they are like equal or not equal. Can I use existing operations to easily convert them back? So if we want, so essentially we want to turn 0 into 1 and -1 into, so when we call the built-in, we do a signed integer comparison. This pushes -1, 0, or 1 onto the stack. We want to turn 0 into 1 and -1, 1 into 0. They're like a nice trick we can do to accomplish that, or do we need to write our own built-in? So we can multiply them. Let's just write our own built-in. So we need to write built-ins. So what we want to write is our own built-in, a runtime built-in. Its name is equal int. It takes 2 arguments, 1 output. It has the, we allow constant following, why not? Its name is equal int, and we don't have any other built-in. Do I have dispatch? Dispatch. So this is essentially the minimum stuff you need to write to essentially add your own instruction into love. And this is just does nothing. Like it is called and then immediately jumps to the next instruction. So what we first need to do is we get the two input values. So we access the stack and get the values out. This is an incomplete type because we need to define it. So the stack goes down, which means that the value that was pushed first is at index 1, which is the left-hand side, and the one that is then, so stack looks like ls, rs, and we want to turn that into LHS equals RSS, which means that, and the way the stack goes, like vstack pointer 1 is this index, and that's a vstack pointer 0. So now we just compare the two integer values and push them, adjust the stack pointer. So we need to push it one back, and then we write the result back as an integer onto the stack. Let's do like that. So this is now our built-in, which means that instead of calling the provided one, we simply call our built-in equal int. And when I compile it now, we don't getting any assertion failure. The debug assembly doesn't know how to handle it, but that's fine. But as you can see, we push 0, we push 0, we're calling our built-in, and then we're calling assert. And since we are successfully returning, 0 must in fact have been equal to 0. So that's great. I find it interesting that it didn't constant fold them. Because 0 to 0, right, can be constant folded. Right, we also need to specify that we don't need the process. And now it has in fact been constant folded. So instead of actually like pushing 0, comparing it, we're actually just pushing 1 directly because 0 is in fact equal to 0. So that's nice. Let's commit that. Add integer equality comparison. So now I've prepared a test case. We can run it and integer constant. And what I have to do is get this test to pass. I find it very interesting that the first, because we already, so the parsing code already handles all of this one, because they parse in our current case, and then it trips out right here when we have the hexadecimal digits. So let's, before we end it today, really go ahead and support the other bases of integer values. Integer constant expression. So we've got decimal digits. We've got octal digits. Let me just write an utility function to integer beyond 6040 in the specified base. Decimal digits is an integer in decimal. Octal digits is an integer in octal. Hex digits is an integer in hex. And binary digits is an integer in binary. And then when we have, in fact, we need the appropriate prefix here. So if we have x, or if we have capital X, it's hex. If we have B or capital B, it's binary. And So when we here 0, so when we have 0, we do something, otherwise we pass decimal digits. So if we have 0, we either pass hex, binary digits, or octal digits. Otherwise, we pass decimal digits. Is that enough to make the test pass? No. Because here we're consuming a 0, and if we only have 0, then we, right? So we're saying if we have 0, try to pass this one. So, for example, 0xa, we pass 0, then we pass 0, means we go here, then we go to hex digits, which passes an x, which passes an hex integer. But of course, if we're only having 0, we're saying we pass 0, okay? And now we pass one of those. In this case, we don't have an x, we don't have a b, so we pass octal digits, we don't have any digits left, so return. But we haven't actually, or rather, we don't have digits left, so we fail, right? So an octal digit, what do we do? Can be optional, right? That's the easiest way. So 0 on its own is a valid number, in which case we don't pass hex, we don't pass binary, and we don't pass octal. Instead we get null opt, which we then need to handle here. We're simply saying that if we didn't get any value, this means that we must have the value 0. Yeah. And of course, this is no longer a branch. So else. And this was the wrong thing. That worked fine. However, now we're having the issue right here. So if you have 0 something, so we need to pass digit optional digit separator. Oh, my tests were got all the nice edge cases. So you know what? Let's actually do that a lot easier. Let's say this one is, and just say that we peak the value. So now we are just don't consume a 0 if we have 1, which means that we can just pass it again. So now when we reach a 0, we go into this branch, but we don't consume the 0, so we can pass it again. Which means we don't need this overload. And for reasons this needs a little bit, and different operator precedence. Okay, that's now a lot nicer. So our test passed, which means we now can create integer constants and compare them for equality and assert that they're in fact equal. And in our test file that we're building here, we can do also print stuff, right? So this was our test file. We can print things, and we get a program that actually does stuff. Excellent. So let's commit that. Octal binary integer constant. I believe this is a good breaking point. So I've been streaming for an hour. Thanks for stopping by. Hope to see you again in the next stream, where we will add the remaining arithmetic operators, and then we will start tackling variables. Thank you.